Picture a time before planets, before stars, even before light could travel freely through space. The universe was a swirling, chaotic canvas of heat and darkness, a place where atoms struggled to find each other in the infinite void. And yet, against all odds, something incredible happened. The first complex molecules began to form. These were the building blocks of everything we know today, the fragile seeds of galaxies, life, and even consciousness itself. How did these delicate structures emerge from the cosmic storm? It's one of the greatest mysteries of our existence, and scientists have proposed not one, not 10, but 30 mind-bending theories to explain it. Today, we're diving deep into the cosmos to unravel this enigma, tracing the footsteps of the universe's first chemical whispers. Think about the molecules around you right now, the oxygen in your breath, the carbon in your skin, the water in your cells. Every single one of them has a lineage stretching back to those first fragile bonds forged in the darkness of the early universe. But here's the astonishing part. The conditions back then were nothing short of apocalyptic. Temperatures soared to unimaginable extremes, radiation tore through space, and matter was constantly being ripped apart. So how did anything survive long enough to connect? That's the puzzle we're exploring, and the answers might rewrite what we know about the origins of life itself. This isn't just a story about chemistry, it's a saga of cosmic resilience, a tale of how chaos gave birth to order against all odds. Some theories suggest these molecules formed in the hearts of dying stars, while others point to the icy depths of interstellar clouds. There are even wild ideas involving quantum quirks and dimensions we can't yet perceive. Each possibility opens a door to a universe far stranger and more wondrous than we ever imagined. So if you've ever looked up at the night sky and wondered how it all began, you're about to embark on a journey that will change the way you see reality. The mystery of the universe's first complex molecules isn't just science, it's the origin story of us all. One of the most enduring theories about the birth of complex molecules takes us back to Earth's ancient oceans, a simmering, chaotic brew dubbed the primordial soup. Imagine shallow pools under a sky choked with volcanic ash, lightning crackling through thick clouds, and waves churning with chemicals no living thing had ever touched. In this violent nursery, scientists believe simple molecules like water, ammonia, and methane collided over and over, driven by sheer chance and energy from the environment, until something extraordinary happened. They linked together to form the first building blocks of life. The groundbreaking Miller-Urey experiment in the 1950s brought this idea to life in a lab. By mixing those basic ingredients in a sealed flask and zapping them with electrical sparks to mimic lightning, researchers watched amino acids, the crucial components of proteins, emerge within days. It was a revelation, proving that complex molecules could arise spontaneously from simple chemistry. But here's the catch. While this experiment beautifully explains how life's ingredients might have cooked up on Earth, the universe's first complex molecules likely formed long before our planet even existed. Deep space is far colder, emptier, and more irradiated than those ancient tidal pools. So if the primordial soup theory has a blind spot, it's this: how did molecules survive and evolve in the unforgiving void between the stars? That's where the debate gets fascinating. Some scientists argue Earth's early conditions were just one version of a universal recipe, and similar soups could have simmered on countless worlds. Others point to cosmic rays and interstellar dust as alternative chefs in the kitchen of creation. Either way, the primordial soup hypothesis taught us one vital lesson: complexity can emerge from chaos given enough time and the right ingredients. The question isn't just how life began here, it's whether the universe has been quietly stirring the same pot for billions of years, scattering the seeds of chemistry everywhere. Deep beneath the churning waves of Earth's early oceans, where sunlight never reached and crushing pressures reshaped the very nature of matter, another cradle of creation may have been at work: hydrothermal vents. These towering underwater chimneys, spewing superheated water rich in minerals from the planet's core, create a stark contrast to the primordial soup theory. Here, in complete darkness, the building blocks of life might have assembled not by chance, but through the precise architecture of nature's most extreme chemistry lab. The magic of hydrothermal vents lies in their intricate structure. Picture a porous rock formation, honeycombed with microscopic tunnels, bathed in a constant flow of mineral-laden fluid. These surfaces act like a cosmic assembly line. Charged metal particles attract simple molecules, holding them in place just long enough to bond under intense heat and pressure. The vents create natural temperature gradients too, with scorching 300-degree water at the base cooling rapidly as it rises. This isn't just random chemistry. It's a finely tuned environment where hot and cold zones work together like gears in a machine, driving reactions that would never occur in open water. What makes this theory so compelling are the real-world parallels we've observed. At modern hydrothermal vents, scientists have discovered entire ecosystems thriving in the absence of sunlight, powered purely by chemical energy. But even more astonishing are the complex organic molecules forming there today: amino acids, lipids, even precursors to RNA. If these reactions can happen now, in the harsh conditions of the deep sea, why not 4 billion years ago, when Earth's crust was still young and volcanic activity was far more intense? Critics point out one glaring question: if life's ingredients cooked up in these isolated depths, how did they reach the surface world where life eventually flourished? The answer might lie in the vents themselves. Their explosive activity creates natural convection currents, constantly cycling material between the abyss and shallower waters. It's as if the early Earth had a built-in delivery system, ferrying precious molecular cargo upward over millennia. The hydrothermal vent theory doesn't just offer an alternative to the primordial soup, it suggests that the universe's recipe for complexity might favor extreme environments. From the crushing depths of alien oceans to the mineral-rich geysers on distant moons, the same forces could be at work anywhere heat, chemistry, and time intersect. This isn't merely about how molecules formed on Earth. It's a blueprint for how the cosmos builds, hidden in plain sight beneath the waves. Now let's venture beyond Earth entirely, because what if the universe's first complex molecules didn't form here at all? Enter Panspermia, the electrifying idea that life's ingredients hitched a ride across the cosmos on comets, asteroids, or even interstellar dust. Imagine tiny molecular blueprints forged in the depths of space, surviving epic journeys through radiation and freezing vacuum only to crash land on a young, fertile Earth. It's not science fiction. We've actually found proof in the most unexpected places. Take the Murchison meteorite, a charred space rock that fell over Australia in 1969. When scientists cracked it open, they didn't just find ordinary minerals, they discovered over 90 different amino acids, the same molecules that form proteins in every living cell. Even more astonishing, some of these amino acids had structures never seen on Earth, suggesting they weren't contaminants but genuine extraterrestrial travelers. Similar organic compounds have turned up in comet dust collected by NASA, a Stardust mission, and in the icy plumes of Saturn's moon Enceladus. Suddenly, Panspermia transforms from a fringe idea into a serious question. How much of life's starter kit was delivered to our doorstep by the cosmos itself? But here's where the debate ignites. Even if space rocks carried pre-made molecules to Earth, that doesn't solve the mystery of how those molecules formed in the first place. It simply pushes the question deeper into space, onto the surfaces of asteroids, into the hearts of nebulae, or perhaps within the icy shells of distant protoplanets. Some researchers argue these cosmic ingredients could have cooked up in the frigid emptiness between stars, where icy dust grains act as microscopic laboratories. Others propose they formed near young stars, blasted by intense radiation that paradoxically helped bond atoms together rather than tear them apart. What makes panspermia so compelling isn't just the evidence, it's the scale of possibility. If complex molecules can survive interstellar journeys, then every planet, moon, or comet in the galaxy might share the same chemical ancestry. Imagine a universe where life's building blocks rain down everywhere, turning barren worlds into potential incubators with each meteorite impact. But the theory also raises haunting unknowns. Did Earth's first molecules originate in a distant stellar nursery? Are we all, in some cosmic sense, made of stardust that remembers its way home? The answer might be written in the chemistry of stones from the sky, waiting for us to decode their ancient messages. Lightning doesn't just illuminate the sky, it might have jump-started life itself. Picture Earth's earliest atmosphere, a toxic cocktail of methane, ammonia, and water vapor, devoid of the oxygen we breathe today. Now imagine a storm raging across this alien landscape, bolts of electricity tearing through the thick clouds. Each strike carries enough energy to rip molecules apart and forge them into something new, something complex. This is the essence of electric spark synthesis, the idea that lightning could have been the universe's first chemist, crafting life's ingredients one thunderclap at a time. The science behind this theory is shockingly straightforward. In the 1950s, Stanley Miller and Miller-Urey recreated these primordial storms in glass flasks, filling them with gases thought to dominate Earth's early air. Then came the sparks simulated lightning bursts crackling through the mixture. Within days, the clear liquid turned murky, and when analyzed, it revealed something miraculous: amino acids, the very molecules that form proteins in every living cell. It was as if they'd bottled a piece of the creation process itself. The experiment suggested that lightning didn't just provide energy, it acted like a cosmic sculptor, rearranging simple atoms into the beginnings of biology. But here's where the theory gets even more intriguing. Earth wasn't just struck by the occasional bolt, it was pummeled. Geological evidence suggests our planet endured millions of years of near-constant electrical storms, with lightning flashing up to 1,000 times more frequently than today. That's not just a few sparks in a flask, it's an entire planet-sized laboratory running trillions of simultaneous experiments. Over enough time, with enough energy, even the most unlikely reactions could become inevitable. Critics raise valid questions, though. Could these delicate molecules survive the very storms that created them? Lightning isn't gentle. It generates intense heat and ultraviolet radiation capable of breaking bonds as easily as it forms them. The answer might lie in the aftermath. After the flashes faded, rain would have washed these newly minted compounds into pools and oceans, shielding them from further destruction. It's a cycle as old as the hills, destruction giving way to creation, chaos birthing order. Electric spark synthesis doesn't just explain how molecules formed, it hints at something deeper about the universe's design. Lightning isn't unique to Earth. We've observed titanic storms on Jupiter, Venus, even distant exoplanets. If a passing thunderstorm could lay the groundwork for life here, why not on worlds we've yet to discover? The same bolts that once terrified our ancestors might hold the key to understanding our cosmic roots, proving that sometimes the spark of creation comes from the most electrifying places. The young sun didn't just warm the early Earth, it bombarded it with a relentless barrage of ultraviolet light, far more intense than anything we experience today. While this might sound like a recipe for destruction, that very radiation could have been the catalyst for life's first delicate molecules. Picture a planet bathed in an eerie glow, its thin atmosphere offering little protection as UV rays sliced through the air, striking molecules with enough energy to tear them apart and reassemble them into something new. In this harsh environment, destruction and creation were two sides of the same cosmic coin. Laboratory experiments have shown just how powerful this process could be. When scientists expose simple gases like methane, water vapor, and carbon dioxide to intense UV light under conditions mimicking Earth's early atmosphere, something remarkable happens. Complex organic compounds begin to form. Sugars, amino acids, even the nucleobases that make up DNA have all been synthesized this way, as if sunlight itself were an invisible chemist. The key lies in the energy of UV radiation, which doesn't just break bonds at random. Instead, it acts like a precision scalpel, snipping molecules in exactly the right places to allow new, more intricate structures to emerge. But how do these fragile molecules survive such brutal conditions? The answer might lie in the shadows. On the early Earth, shallow pools or the undersides of rocks could have served as natural shelters, allowing newly formed compounds to accumulate while being shielded from further radiation. Even more intriguing, certain minerals like zinc sulfide, common in volcanic regions, have been found to absorb UV light and re-emit it at lower, less destructive energies, effectively turning harsh radiation into a gentler, more constructive force. The implications stretch far beyond our own planet. UV catalysis isn't unique to Earth. Every young star floods its surroundings with similar radiation. This means the same chemical reactions could be unfolding right now on distant exoplanets, their atmospheres or surfaces quietly assembling the building blocks of life under the glow of alien suns. It's a humbling thought. The same light that gives us sunburns might be one of the universe's most prolific architects, weaving complexity out of simplicity, one photon at a time. Among the chaos of early Earth's chemical experiments, one of the quietest players might have been the most influential: ordinary clay. These unassuming minerals, formed by the weathering of volcanic rock, possessed a hidden talent. Their microscopic layers acted like nature's first assembly lines, guiding simple molecules into intricate patterns. Picture a landscape where rain and wind have ground stone into fine particles, creating tiny landscapes of ridges and valleys at the atomic scale. These surfaces didn't just passively exist, they actively curated chemistry, offering pockets of order in a world drowning in randomness. The magic of clay lies in its structure. Each flake is made up of stacked sheets with negative charges spread across their surfaces like a grid of tiny magnets. When amino acids or other building blocks washed over these sheets, the charged spots grabbed hold of them, aligning molecules in precise arrangements. Think of it like a puzzle board holding pieces in place until they snap together into something greater. Over time, these trapped molecules could have linked up to form polymerase chains that resemble the proteins and genetic material found in all living things. Remarkably, clays don't just organize, they also protect. Their layers shield delicate bonds from destructive forces like ultraviolet radiation or sudden temperature swings, giving fragile chemistry a fighting chance to grow more elaborate. Laboratory tests have proven this isn't just speculation. When scientists mix clays with simple organic compounds under conditions mimicking early Earth, the minerals consistently coax those compounds into longer, more complex chains. Some clays, like montmorillonite, even accelerate reactions by a factor of 100, acting as natural catalysts. But the most startling discovery came when researchers observed certain clays not just assembling molecules but copying patterns. The mineral's surface can template specific sequences, encouraging new molecules to line up in mirror images of existing ones. It's a ghostly echo of replication, the very process that defines life. Critics argue that while clays excel at organization, they lack the specificity of true biological systems, yet their imperfections might actually be their strength. Early Earth wasn't a sterile lab. It was a messy, improvisational workshop where good enough often trumped perfect. Clay's versatility could have allowed countless chemical experiments to run simultaneously, with the most successful combinations eventually breaking free to evolve independently. This theory doesn't just rewrite life's origin story, it expands where we might look for its beginnings. clay-rich environments exist on Mars, in the icy fractures of Europa's seafloor, even in the clouds of Venus. If a humble mineral scaffolded life here, why not elsewhere? The universe's first complex molecules might not have been forged in fire or ice, but in the quiet, patient spaces between layers of rock, where chemistry found its footing one careful step at a time. In the frozen vastness between stars, where temperatures plunge hundreds of degrees below zero, something counterintuitive unfolds. Deep cold becomes an unlikely architect of complexity. Far from being a sterile wasteland, interstellar ice grains act as microscopic laboratories, their frozen surfaces hosting chemical reactions that defy earthly logic. Picture a speck of dust smaller than a snowflake drifting through a nebula's swirling gases. Over millennia, molecules like water, carbon monoxide, and ammonia freeze onto its surface, forming an icy shell just a few atoms thick. To us, this seems inert, but when bathed in cosmic radiation, these ice mantles transform into bustling factories of molecular creation. The secret lies in the unique physics of extreme cold. At temperatures nearing absolute zero, molecules move sluggishly, almost as if trapped in cosmic amber. This sluggishness is a gift. It gives atoms time to find the perfect alignment before bonding, reducing the chaos of random collisions that dominate warmer environments. Even more crucial is the role of radiation. When high-energy particles from supernova or young stars slam into these ice grains, they don't just destroy, they rearrange. The energy blast knocks electrons loose, creating reactive fragments that scurry across the ice until they collide and fuse into something entirely new. Remarkably, these reactions favor complexity. Experiments mimicking these conditions have produced amino acids, sugars, and even the nucleobase uracil, a key component of RNA, all from simple ices zapped with radiation. But why does space ice succeed where Earth's chemistry struggles? The answer might be tunneling, a quantum effect where particles bypass energy barriers entirely. On Earth, heat usually drives reactions, but many vital bonds require more energy than ambient temperatures provide. In the frigid void, quantum mechanics takes over. Hydrogen atoms, for example, can literally tunnel through barriers to bond with other molecules, a process impossible under normal conditions. It's as if the universe cheats its own rules to build complexity where none should exist. The proof isn't just theoretical. Telescopes have detected the chemical fingerprints of complex organics in protoplanetary disks and comets. The Rosetta mission found glycine, the simplest amino acid, on Comet 67P, while ALMA observatory data reveals molecules like methanol and formaldehyde swirling around infant star systems. These discoveries suggest that ice grain chemistry isn't rare, it's universal. Every newborn planet might be seeded with prefabricated molecular kits delivered by comets or asteroids coated in these irradiated ices. This theory reshapes our search for life's origins. Instead of imagining a warm little pond, we might need to envision a cosmic deep freeze, where the building blocks of biology assembled long before reaching any planet. The same processes could be unfolding right now in Orion's molecular clouds or the icy rings of Saturn, silent, slow, and inexorable. If ice grains truly are the universe's first chemists, then life's ingredients may be as common as stardust, waiting only for the right world to thaw them into being. Beneath the roiling oceans and trembling crust of early Earth, another kind of storm was brewing, one that might have forged the ingredients of life in the scorching breath of volcanoes. These weren't the picturesque cones we know today, but titanic vents spewing gases at temperatures that could melt rock, creating a chemical playground where sulfur, nitrogen, and carbon dioxide collided in a frenzied dance. While we often think of volcanoes as forces of destruction, they may have been the universe's first alchemists, transforming simple elements into the building blocks of biology. The magic begins with the gases themselves. When magma rises from Earth's mantle, it carries more than just molten rock. It's laced with volatile compounds like hydrogen sulfide, ammonia, and carbon monoxide. As these gases erupt into the cooler surface environment, something extraordinary happens. The sudden temperature drop triggers a cascade of reactions, much like steam condensing into water, except here the products are far more complex. Sulfur, often dismissed as a poison, plays a starring role. Its unique chemistry allows it to act like a molecular glue, bridging gaps between other atoms and stabilizing fragile intermediate compounds. Nitrogen, released as ammonia, provides the backbone for amino acids, while carbon monoxide and dioxide become the raw material for every organic structure. Laboratory experiments have recreated these conditions with astonishing results. When scientists simulate volcanic gas mixtures in pressurized chambers, subjecting them to heat and electrical discharges mimicking lightning near eruptions, organic molecules form at a staggering rate. Pyruvic acid, a critical compound in modern metabolism, emerges alongside formaldehyde and even simple sugars. These reactions aren't rare or delicate, they're robust, thriving in the very chaos that would seem hostile to order. What's more, volcanic minerals like iron and nickel sulfides act as natural catalysts, accelerating the process without being consumed, like molecular blacksmiths hammering atoms into place. The real power of this theory lies in its scalability. Early Earth wasn't dotted with the occasional volcano, it was a global network of them, with eruptions hundreds of times more frequent than today. Each event would have pumped out not just lava, but vast plumes of gas that mingled in the atmosphere, rained down as chemical-rich precipitation, or pooled in volcanic hot springs. These environments create a perfect gradient, scorching at the vent's mouth, cooler just a few feet away, allowing different reactions to occur in sequence as molecules journey from extreme heat to moderate temperatures. But volcanoes offer another gift: protection. Their ash clouds shield newly formed compounds from the sun's punishing ultraviolet rays, while acidic pools around fumaroles preserve delicate molecules by preventing degradation. It's a self-sustaining system where destruction fuels creation, and where the same forces that once shaped our planet's surface might have also shaped its destiny. This isn't just an Earth-bound phenomenon. Volcanic activity has been detected on Io, Mars, even distant exoplanets. If gas reactions here birthed life's precursors, why not on worlds where lava flows stretch for thousands of miles? The universe's first complex molecules might not have needed gentle ponds or icy grains, just the fiery breath of a restless planet, turning poison into possibility one eruption at a time. Deep beneath our feet, where sunlight never reaches and the pressure could crush steel, an invisible force was at work: radioactivity. In the cracks and pores of Earth's crust, unstable elements like uranium and thorium have been decaying for billions of years, releasing energy in slow, steady pulses. While we often think of radiation as destructive, what if these atomic breakdowns were actually the universe's way of jump-starting complexity? Imagine microscopic particles zipping through water-filled crevices, each carrying enough energy to tear molecules apart. But instead of chaos, this demolition creates opportunities. The broken pieces reassemble into something new, something intricate. This is radiolysis, nature's own atomic forge, and it might hold the key to life's molecular origins. The process is deceptively simple yet profoundly elegant. When radioactive particles collide with water, something abundant in Earth's early crust, they split it into highly reactive fragments: hydrogen gas, hydrogen peroxide, and free radicals. These fragments don't linger idly. They're molecular sharks hungry to bond with anything nearby. If the environment contains carbon or nitrogen, say from volcanic gases seeping through rock, these reactive fragments latch on, building organic compounds piece by piece. Remarkably, this isn't theoretical. In labs, scientists have recreated these conditions, bombarding water and simple gases with radiation, only to find amino acids and carboxylic acids forming reliably. Even more compelling, the same reactions occur in nature today. In places like South Africa's Moab Kotsong mine, 2 miles underground, researchers have detected complex organic molecules thriving near uranium-rich deposits, as if the rocks themselves are quietly assembling life's ingredients. But why does radioactivity succeed where other energy sources fail? The answer lies in consistency. Unlike lightning or UV rays, which are sporadic and uneven, radioactive decay delivers a steady drumbeat of energy for millions of years. It's not a brief spark but a marathon, giving reactions time to build complexity gradually. There's also a built-in protection mechanism. Deep underground, radiation's products are shielded from surface hazards like ultraviolet light or atmospheric erosion. The crust becomes a natural incubator where fragile molecules can grow bolder over epochs without being wiped out by planetary chaos. The implications stretch far beyond Earth. Radioactive elements are common in the cosmos, found in asteroids, Martian soil, even the icy shells of moons like Europa. If radiolysis works here, why not in these places? Some of the most tantalizing evidence comes from meteorites. The Murchison meteorite, packed with amino acids, also contains traces of aluminum-26, a radioactive isotope known to release energy as it decays. Coincidence or a clue that the universe has been using radioactivity as a universal chemistry set? Perhaps the most radical idea is that radiation's role wasn't just energetic, it might have been directional. Certain radioactive minerals, like zircon, have crystal structures that act like molecular templates, aligning reactants in ways that favor specific outcomes. It's as if the universe didn't just provide energy, it provided a blueprint guiding randomness toward order. This isn't just about how molecules formed, it's about how they formed with purpose, as if the cosmos was always leaning toward life. So next time you hear about radiation's dangers, remember, the same force that requires lead shielding today might have been the quiet architect of existence, turning rock and water into biology's first whispers. The universe works in paradoxes: destruction birthing creation, chaos yielding precision. And deep in the darkness, where atoms shatter and reassemble, we might find the most profound truth of all, that even decay can build. Along coastlines where land meets sea, the rhythmic dance of tides creates a natural laboratory for chemistry, one that might hold clues to life's molecular beginnings. Tidal pools, those shallow basins carved into rock, become traps for seawater during low tide, leaving behind a concentrated soup of dissolved minerals and organic compounds. As the water evaporates under the sun's glare, something remarkable happens. Molecules that once drifted apart in the vast ocean are forced into close quarters, bumping into each other with increasing frequency. This isn't just random mixing, it's nature's way of turning up the odds on complexity. The magic of tidal pools lies in their cycles of repetition. Each high tide brings a fresh influx of raw materials, amino acids, nucleotides, lipids, while each low tide strands them in shrinking puddles where evaporation works like an invisible hand, squeezing molecules together. Laboratory experiments mimicking these conditions have shown that this cycle of dilution and concentration can drive polymerization, the process where small molecules link into long chains. For instance, when amino acids are repeatedly wetted and dried, they form peptide bonds, the same connections found in proteins. It's as if the tides themselves are stirring a primordial pot, adding ingredients and reducing the broth until something new emerges. But concentration alone isn't the full story. Tidal pools also offer a gradient of environments, sun-baked edges where reactions accelerate under heat and UV light, cooler depths where delicate structures stabilize, and mineral-rich surfaces that act as catalysts. Some rocks contain clays or metal ions that lower the energy needed for bonds to form, effectively giving molecules a leg up. Even the salt content plays a role. As water evaporates, salinity spikes, creating conditions that can shield certain compounds from degradation while destabilizing others, a molecular survival of the fittest. Critics point out that tidal pools are volatile places, subject to sudden storms or temperature swings that could dismantle fragile polymers. Yet this volatility might be precisely what made them effective. Just as evolution relies on both mutation and selection, tidal pools provide chaos to generate novelty in order to preserve success. Molecules that could withstand the harsh shifts, perhaps by folding into stable shapes or forming protective shells, would persist while others reset for another attempt. The implications stretch beyond Earth. Mars once had vast oceans, and its shorelines might have harbored similar pools. Even Saturn's moon Titan, with its methane lakes, could have analogues where organic compounds concentrate under alien tides. The universe may favor these liminal spaces where push and pull, wet and dry, creation and destruction balance on a razor's edge. In tidal pools, the boundary between chemistry and biology blurs not with a sudden leap, but through countless cycles, each ripple adding another stitch to the fabric of life. When asteroids slam into a planet, they don't just leave craters, they unleash enough energy to rewrite chemistry itself. Picture a space rock the size of a mountain screaming through the atmosphere at 50 times the speed of sound, hitting the ground with the force of 1,000,000 nuclear bombs. In that apocalyptic instant, temperatures soar beyond 10,000 degrees, pressures spike to levels found deep inside stars, and shockwaves ripple through the surrounding rock like tsunamis of pure force. Yet from this violence, something miraculous emerges. A fleeting window where atoms are forced together so violently that they forge bonds nature could never achieve under normal conditions. This is meteorite impact synthesis, the idea that life's building blocks might have been hammered into existence by celestial collisions. The evidence comes from both the lab and the field. Scientists have recreated impact conditions using high-powered guns and lasers, firing projectiles at targets containing simple mixtures of water, ammonia, and carbon dioxide compounds abundant on early Earth. The results are staggering. Within microseconds, the shockwaves transform these basic ingredients into complex organics. Amino acids like glycine, nucleotide bases like adenine, even fatty acids that could form primitive cell membranes. The same reactions have been spotted in nature. The Sudbury impact structure in Canada, forged 2 billion years ago by a colossal asteroid, contains layers rich in organic carbon. Even more compelling, meteorites themselves often carry these compounds, suggesting impacts didn't just create molecules, they also delivered them. But how could anything survive such extreme conditions? The key lies in the aftermath. While the initial impact vaporizes rock, the expanding shockwave creates concentric zones of decreasing intensity. At the outer edges, temperatures and pressures drop just enough to allow newly formed molecules to stabilize before they're destroyed. It's like a cosmic Goldilocks effect: too little energy and nothing reacts, too much and everything disintegrates, but in that narrow band between, complexity flourishes. Some studies suggest these zones could span miles around a large impact, creating vast temporary reactors where chemistry runs wild. The implications are staggering. Early Earth endured a period called the Late Heavy Bombardment, where asteroids rained down for hundreds of millions of years. Far from sterilizing the planet, this onslaught might have been the universe's most violent chemistry set, churning out molecular diversity on a global scale. Even more mind-bending, this process isn't unique to Earth. Mars shows evidence of similar impacts, and its soil contains organic molecules detected by rovers. Europa's ice shell bears scars from comet strikes that could have mixed surface organics with subsurface oceans. The same fiery birthright might extend across the cosmos, written in the scars of countless worlds. Critics argue that impact sites would be too chaotic for sustained chemistry, but nature offers a counterpoint. In the Chicxulub crater, The dinosaur-killing impact in Mexico, scientists have found hydrothermal systems that persisted for millennia after the collision. These zones, heated by underground magma, could have refined impact-generated molecules, filtering out the fragile ones while amplifying the robust. It's a one-two punch. First, the asteroid provides the energy to create, then the planet provides the time to perfect. What makes this theory so profound is its duality. Impacts are both destroyers and creators, erasing worlds in one breath while seeding them with life's potential in the next. Every crater tells two stories: an ending and just maybe a beginning. The universe doesn't play favorites. It sculpts with the same violent brushstrokes across the canvas of space, turning catastrophe into creation with bewildering indifference. So next time you see a shooting star, remember, what looks like destruction from afar might be the universe's way of stirring the pot, mixing atoms until something new, something alive, dawns from the chaos. Deep beneath the planet's surface, where tectonic plates grind together and the weight of entire oceans presses down on rock, lies a hidden crucible of creation. Here, in the crushing embrace of Earth's mantle, pressures soar to levels that distort the very rules of chemistry. Atoms behave differently under such extremes. Bonds form that would never survive at the surface. Molecules twist into unfamiliar shapes, and reactions unfold at speeds defying ordinary physics. This is the realm of deep Earth pressure chemistry, where the universe's first complex molecules might have been forged not in gentle pools or icy voids, but in the planet's own relentless grip. Experiments simulating these conditions reveal just how transformative pressure can be. In diamond anvil cells, devices that squeeze samples between the hardest known material, scientists have watched simple carbon and hydrogen compounds morph into complex organics under pressures exceeding 50,000 times Earth's surface atmosphere. Methane, a humble molecule often dismissed as chemically inert, polymerizes into long hydrocarbon chains. Water doesn't just freeze, it forms exotic ices with structures that act as molecular scaffolds, guiding other compounds into precise arrangements. Even nitrogen, typically reluctant to bond, gets coaxed into ammonia-like compounds that could feed prebiotic chemistry. The deeper you go, the more the periodic table seems to rewrite itself. The real magic happens in subduction zones, where oceanic plates dive beneath continents. As rock descends, it carries surface materials, water, carbon dioxide, minerals into the abyss. These ingredients, compressed and heated over millennia, undergo reactions impossible anywhere else. Iron-rich minerals catalyze transformations, sulfur acts as a molecular bridge, and the sheer density of the environment forces atoms so close together that they can't help but link up. Some researchers believe this process could explain the mysterious carbon-rich fluids found spewing from deep-sea vents, fluids packed with organic molecules that seem to emerge from nowhere. But how could these deep Earth creations ever reach the surface? The answer lies in the planet's restless nature. Volcanic plumes act like elevators, ferrying material from the mantle to the crust in a matter of days. Hydrothermal vents, fed by subterranean fluids, become portals for this chemistry to leak into the oceans. Even earthquakes play a role, fracturing rock and creating pathways for pressurized fluids to surge upward. It's a planetary-scale recycling system, where destruction below fuels creation above. What makes this theory so compelling is its universality. High-pressure environments exist on icy moons like Europa, within the cores of gas giants, even in the remnants of shattered planets orbiting distant stars. If Earth's depths could cook up complexity, why not elsewhere? The same forces that build mountains and fuel volcanoes might also be silent architects of life, turning the underworld into a workshop where molecules learn to survive and thrive under pressure. The early Earth sky might not have been blue at all. Instead, imagine a thick, orange-brown haze hanging over the landscape like an eternal twilight, a photochemical smog so dense it would make modern city pollution look tame. This eerie shroud, rich in methane and ammonia, didn't just obscure the sun. It acted as a vast chemical reactor, brewing complex molecules in plain sight. While today we associate smog with environmental harm, billions of years ago, it could have been the cradle of life's first building blocks. The process begins when sunlight, especially ultraviolet rays, slams into methane molecules in the upper atmosphere, breaking them apart into reactive fragments. These fragments, hungry for new bonds, collide with ammonia and water vapor, forming compounds like formaldehyde and hydrogen cyanide. These aren't just random byproducts, they're the raw materials for amino acids and nucleobases, the very stuff of life. What makes this theory so compelling is Titan, Saturn's largest moon, where a nearly identical process unfolds today. Titan's atmosphere, thick with nitrogen and methane, is bathed in a perpetual orange haze, a photochemical smog factory raining organic compounds onto its surface. NASA Cassini mission detected molecules like benzene and complex hydrocarbons floating in this haze, some linking into chains hundreds of atoms long. If Titan's atmosphere can create such complexity without liquid water or volcanic activity, why couldn't Earth have done the same? The parallels are uncanny, suggesting a universal recipe where sunlight and simple gases conspire to build complexity. Yet Earth's smog would have had one critical advantage: water. While Titan's organics accumulate in frozen dunes or methane lakes, Earth's haze particles would have been washed into oceans and lakes by rain, creating concentrated pools where reactions could continue. Laboratory experiments back this up. When scientists simulate early Earth smog in chambers and then rinse the resulting goo with water, they find it teeming with amino acids and sugars. The smog acts like a prebiotic delivery system, synthesizing molecules in the sky and depositing them where they're most useful. Critics point out that smog-derived organics would face brutal UV radiation at high altitudes, potentially breaking apart faster than they could assemble. But here's the twist: the haze itself provides shade. As the smog thickens, it absorbs harmful rays, creating a self-regulating shield that protects the very molecules it produces. It's a perfect balance, just enough sunlight to drive reactions, but not so much that it destroys the products. The implications stretch far beyond our planet. If photochemical smog is a universal pathway, then any world with methane, nitrogen, and sunlight might be cooking up life's ingredients right now. From the hazy skies of exoplanets to the methane-rich atmospheres of distant moons, the universe could be full of orange skies quietly assembling the pieces of life. Earth's ancient smog might seem like a relic of a dead world, but in reality, it could be the most common chemistry set in the cosmos, turning poison into possibility, one photon at a time. At the coldest edges of the universe, where temperatures hover just above absolute zero, chemistry should grind to a halt. Yet somehow it doesn't. Molecules still form, atoms still bond, and complexity emerges in places that defy classical logic. The secret might lie in one of quantum mechanics' most bizarre phenomena: tunneling. Imagine a snowball rolling toward a hill too steep to climb. In our everyday world, it would stop dead. But in the quantum realm, that snowball has a chance to vanish from one side of the hill and reappear on the other, as if the obstacle never existed. This isn't magic, it's the universe's own cheat code, allowing particles to bypass energy barriers that should be impossible to overcome. In the frozen depths of interstellar space, this quantum sleight of hand could explain how delicate reactions occur. Take hydrogen, the universe's simplest atom. Under normal conditions, two hydrogen atoms need a significant burst of energy to fuse into molecular hydrogen. But in frigid molecular clouds, where heat is virtually non-existent, tunneling provides a shortcut. The atom's wave functions, their fuzzy quantum identities overlap just enough to let them leak through the barrier, bonding without the required energy. Experiments confirm this. When scientists chilled hydrogen gas to near absolute zero, molecular hydrogen formed far faster than classical chemistry predicted. Tunneling isn't a rare exception, it's a ghostly hand guiding reactions where no hand should reach. The implications grow even stranger when applied to life's building blocks. Formaldehyde, a precursor to sugars, has been detected in icy space clouds. Classical models struggle to explain its abundance in such cold environments, but tunneling bridges the gap. A carbon monoxide molecule and a hydrogen atom, normally too sluggish to react, could quantum mechanically sidestep the energy deficit, stitching themselves together into something more complex. Even water, a molecule essential for life, might owe its cosmic prevalence to tunneling. Oxygen and hydrogen, frozen on dust grains, could have circumvented their activation energy through this effect, assembling ice mantles that later melted into oceans. Critics argue that tunneling is too probabilistic to drive large-scale chemistry, yet nature has time millions of years and space countless dust grains on its side. What seems improbable in a lab becomes inevitable across light years. Recent studies even suggest tunneling could explain the chirality of life's molecules. Many organic compounds exist in mirror image forms, but life overwhelmingly uses one. Quantum interactions with polarized starlight might have tipped the scales, favoring certain tunneling pathways over others. It's as if the universe's quirks wrote bias into the recipe of existence. This theory doesn't just rewrite chemistry, it redefines where life could begin. If quantum tunneling operates in the icy shells of Europa or the methane lakes of Titan, then the coldest corners of the cosmos might be buzzing with covert molecular activity. The same laws that let electrons dance through semiconductors could have silently assembled life's first pieces, proving that sometimes the universe doesn't break the rules, it tunnels right under them. Deep beneath the ocean's surface, where scalding water meets jagged rock, a humble mineral might hold the key to life's origins. The iron-sulfur world hypothesis turns the spotlight on simple compounds like pyrite fool's gold, and their uncanny ability to kickstart chemistry in ways no one expected. These metallic crystals, forged in the searing heat of hydrothermal vents, don't just sit idly by. They act like nature's first enzymes, their surfaces bristling with reactive sites where molecules are pulled apart and reassembled with almost biological precision. It's as if the universe embedded cheat codes into these rusty rocks, giving them the power to orchestrate reactions that would otherwise stall without a push. The magic lies in iron and sulfur's unique partnership. When these elements form clusters, their alternating atomic structure creates pockets of positive and negative charge perfect for gripping passing molecules and bending them into new shapes. Modern cells still rely on iron-sulfur proteins to perform critical tasks like converting nutrients into energy, a clue that this partnership might be ancient. But here's the twist. In the vent's labyrinth of mineral chimneys, these reactions could happen without any biology at all. Lab experiments show that iron-sulfur minerals catalyze reactions strikingly similar to steps in the Krebs cycle, the metabolic engine powering all living cells. It's a haunting overlap, non-living rocks performing chemistry that mirrors life's core processes. What makes this theory revolutionary is its simplicity. Unlike theories requiring elaborate setups or rare conditions, the iron-sulfur world operates on geology's default settings. Vents spew these minerals constantly, their porous structures offering endless nooks for molecules to gather and react. The vent's temperature gradients add another layer of finesse. Scorching water rising from below drives reactions, while cooler regions nearby let products stabilize. It's a self-regulating system where chemistry escalates step by step, from simple gases like carbon monoxide to complex organics like acetic acid. Critics question whether these mineral-catalyzed reactions could truly bridge the gap to biology. But recent discoveries add weight to the idea. In the Lost City hydrothermal field, a ghostly white vent system in the Atlantic, scientists found organic molecules forming abiotically on iron-sulfur surfaces. Even more compelling, some vent minerals can replicate a primitive form of electron transport, the same process cells use to generate energy. If geology invented metabolism before life even existed, then the leap to biology might not have been a leap at all, but a small, inevitable step. This isn't just about Earth's history. Mars once had hydrothermal systems, and Europa's ocean likely hosts them today. If iron-sulfur chemistry paved the way for life here, why not across the cosmos? The universe might be teeming with these metallic catalysts, quietly assembling life's framework in the dark. The iron-sulfur world doesn't just explain how life began. It suggests the cosmos was always primed to create it, one chemical whisper at a time. Cosmic rays, those high-energy particles streaking across the universe at nearly the speed of light, aren't just celestial curiosities. They might be the invisible sculptors of molecular complexity, shaping the building blocks of life with each collision. Picture a proton stripped from a distant supernova, hurtling through space until it slams into a simple molecule floating in a nebula. The impact doesn't just shatter the molecule, it supercharges it, leaving behind a trail of ionized fragments desperate to rebond. In the chaos of these high-energy crashes, something remarkable happens. Atoms rearrange into configurations that would never form under gentler conditions, stitching together the first threads of organic complexity. The evidence lies in the icy grains of interstellar space. When cosmic rays punch through these frozen particles, they don't just leave damage, they create opportunity. The energy deposited by a single cosmic ray can rip apart water ice, freeing oxygen and hydrogen atoms that immediately seek new partners. Carbon monoxide, normally a reluctant participant in reactions, gets transformed into reactive ions that eagerly bond with nitrogen or sulfur. Experiments simulating these interactions in labs have produced glycine, the simplest amino acid, alongside rudimentary sugars and even nucleotide bases. It's as if the universe's most violent particles are also its most gifted chemists, turning frozen wastelands into molecular factories. But cosmic rays don't just work in deep space, they're catalysts on planetary surfaces too. Early Earth, lacking a robust magnetic field and thick atmosphere, would have been bombarded by these particles at rates 100 times higher than today. When they struck methane-rich puddles or ammonia-laced tidal flats, the energy could have sparked chains of reactions similar to those in interstellar ice. Unlike lightning or UV radiation, cosmic rays penetrate far deeper, reaching underground water reservoirs or cave systems where newly formed molecules might be sheltered from surface hazards. Some researchers even speculate that cosmic ray showers could explain the sudden bursts of complexity found in certain ancient rock layers, geological signatures of moments when the sky itself jump-started chemistry. What sets cosmic rays apart is their universality. They rain down on Mars' barren plains, Europa's icy shell, even the atmospheres of gas giants. If they can drive prebiotic chemistry here, why not across the cosmos? The same particles that pose a radiation hazard to astronauts today might have been the silent architects of life's blueprint, proving that destruction and creation are two sides of the same cosmic coin. Yet the story isn't without twists. While cosmic rays excel at initiating reactions, their randomness poses a puzzle. How did fragile molecules survive long enough to accumulate? The answer might lie in nature's buffers, clay minerals that trap and protect organics, or hydrothermal vents that recycle radiation's products into stable configurations. It's a delicate dance. Cosmic rays provide the spark, and planetary environments provide the crucible. This theory doesn't just reshape our search for life's origins, it redefines where we look. The next amino acid forming in a distant nebula, the next sugar molecule assembling on a frozen moon, might owe its existence to a particle born in a star's death throes. The universe writes its recipes in radiation, and every cosmic ray carries a whisper of that ancient, invisible hand. high above Earth's surface, where the air thins and sunlight fractures into dazzling hues, an invisible fleet of particles drifts, each one a potential cradle for cosmic chemistry. Atmospheric aerosols, those microscopic motes of dust, salt, and ash, are far more than passive flecks in the sky. They're dynamic micro-reactors, bustling with activity on a scale so small it defies imagination. Picture a single grain of sea salt lofted into the air by ocean spray, its surface pocked with microscopic craters and ridges. To our eyes, it's a speck. To molecules, it's a sprawling landscape of valleys where water, sulfur, and carbon dioxide gather in concentrated pockets, colliding with frequencies impossible in open air. This isn't just dust, it's the universe's way of turning the atmosphere into a chemistry set. The magic hinges on surface area. A single cubic centimeter of air might hold thousands of aerosols, each offering nooks and crannies where reactants can cling and interact. In the early Earth's haze-filled skies, these particles would have been coated with sticky films of water and organic compounds, creating droplets so tiny they behave unlike any liquid we know. Here, chemistry accelerates. Reactions that would take years in a test tube unfold in hours, driven by the unique physics of microscopic confinement. Lab experiments confirm this. When scientists simulate prebiotic conditions in aerosol chambers, amino acids form at rates 1,000 times faster than in bulk solution. It's as if the molecules themselves feel the urgency of cramped quarters, finding partners before evaporation or radiation can pull them apart. But aerosols offer another gift: protection. High in the atmosphere, UV rays and cosmic radiation would shred fragile organics unless they're tucked inside these floating sanctuaries. The outer layers of an aerosol droplet can absorb harmful energy, sacrificing themselves like molecular armor while the compounds at the core remain unscathed. Some particles even self-organize, with fatty acids arranging into primitive membranes that mimic cell walls, shielding their cargo from the elements. This duality, intense reactivity paired with unexpected durability, makes aerosols ideal incubators for complexity. The real-world parallels are striking. Today, scientists detect complex organics in atmospheric dust over rainforests and deserts, proof that this process never stopped. Even interstellar space hosts similar particles, cosmic aerosols, where icy mantles foster reactions in the void. The implications are staggering. If Earth's skies were alchemists, then every planet with an atmosphere might be running the same experiment. Venus' sulfuric acid clouds, Jupiter's ammonia storms, even the hydrocarbon haze of Titan could all be quietly assembling life's ingredients, one microscopic collision at a time. Critics argue that aerosols lack the stability for sustained chemistry, but nature finds a way. Some particles linger for weeks, cycling between day and night, wet and dry, allowing reactions to proceed in stages. Others clump into larger aggregates, creating intricate gradients where different chemistries unfold in layers. And when rain finally washes them to the surface, they deliver their molecular bounty to ponds and oceans, seeding environments where complexity can flourish. This theory doesn't just reshape our view of life's origins, it elevates the mundane to the miraculous. The same haze that dims city skylines or paints sunsets crimson might have once been the scaffolding for existence itself. From the dust of volcanoes to the salt of ancient seas, the universe works in whispers, turning fleeting specks into crucibles where chaos becomes order. Yellowstone's geothermal fields aren't just natural wonders, they're time capsules preserving the violent chemistry of early Earth. Imagine stepping into a landscape where steam hisses from cracked earth, boiling mud bubbles like primordial soup, and mineral-rich water cascades down terraces in blindingly vibrant hues. These extreme environments aren't merely scenic, they're active laboratories where heat, water, and rock conspire to forge molecules in ways that defy conventional chemistry. Here, amid the geysers and fumaroles, scientists have uncovered reactions so strange they rewrite our understanding of how life's building blocks might have assembled. The magic begins with the water itself. Yellowstone's hot springs are more than just heated H2O. They're chemical cocktails laced with sulfur, silica, and metals like iron and manganese. As this scalding fluid surges through underground chambers, it dissolves minerals from the surrounding rock, becoming a supercharged solvent. When these fluids erupt to the surface and cool, something remarkable happens. Dissolved compounds suddenly lose their solubility, precipitating out as intricate crystalline structures. But it's not just inanimate minerals forming. Field studies have detected amino acids and fatty acids clinging to these deposits, as if the very process that builds the park's iconic terraces also assembles organic molecules on the side. Lab experiments simulating these conditions reveal even wilder possibilities. When researchers replicate Yellowstone's alkaline hot springs in pressurized chambers, adding simple gases like carbon monoxide and hydrogen, the results are staggering. Not only do amino acids form, they link into short peptides, the precursors to proteins. Even more astonishing, the mineral surfaces act as templates, favoring certain molecular arrangements over others. It's as if the rocks themselves have preferences, nudging chaos toward order. What makes geothermal fields like Yellowstone so special is their gradient of extremes. A single hot spring might range from near boiling at its vent to tepid at its edges, creating zones where different reactions can unfold in sequence. One area might crack apart water molecules into reactive hydrogen, while another region uses that hydrogen to reduce carbon dioxide into formaldehyde, a critical stepping stone to sugars. The system self-regulates, with convection currents constantly cycling materials between hot and cool zones, allowing stepwise chemistry that would fail in a uniform environment. The implications stretch beyond Earth. Mars' ancient volcanic regions, like Elysium Planitia, bear striking similarities to Yellowstone's terrain, complete with mineral deposits suggesting past hydrothermal activity. Even icy moons like Enceladus, with its subsurface ocean heated by tidal forces, could host similar geothermal systems beneath frozen crusts. If Earth's hot springs can act as molecular factories, why not theirs? Yet geothermal chemistry isn't without its puzzles. How do fragile organic molecules survive the spring's fluctuating acidity and blistering temperatures? The answer might lie in the minerals themselves. Silica deposits, for example, form porous mats that trap and protect organics like microscopic vaults. Iron-rich clays, common around fumaroles, can stabilize reactive compounds long enough for them to grow more complex. Yellowstone doesn't just offer a snapshot of early Earth, it's a living parable about resilience. In waters acidic enough to dissolve nails and temperatures that would kill most life, the universe keeps tinkering, proving that creation isn't always gentle. Sometimes it takes a cauldron. Deep within certain volcanic regions of early Earth, a peculiar mineral seeps from the crack's apatite, a crystalline bearer of phosphorus, an element so rare in the universe yet so vital for life. Without phosphorus, there would be no DNA backbone, no energy-carrying ATP molecules, no cell membranes. But here's the cosmic irony. While phosphorus is essential, it's also notoriously stubborn, often locked away in rocks that refuse to release it. That makes the few places where this element flowed freely nothing short of planetary treasure chests, geological oddities where the universe's rarest puzzle piece was not just present, but actively joining the game of molecular complexity. One such setting might have been the Pilbara region in Australia, where 3.5 billion-year-old rocks tell a tantalizing story. These ancient formations, known as the Dresser Formation, contain veins of whitish minerals rich in phosphates, the reactive form of phosphorus that life can actually use. What's extraordinary is how they got there. Volcanic activity heated groundwater to extremes, allowing it to dissolve phosphorus from deep rocks and concentrate it in shallow pools. Picture these pools as natural soda springs, fizzing with carbon dioxide but also infused with dissolved phosphates. creating a broth where molecules like RNA could have nucleated and thrived. Lab experiments back this up when scientists simulate these phosphate-rich waters, adding simple organic compounds and subjecting them to cycles of wetting and drying. The phosphorus acts like a molecular glue, facilitating bonds between nucleotides that would otherwise never connect. But phosphorus's magic isn't just about availability, it's about chemistry's quirks. On its own, phosphorus is lazy, content to bond with oxygen in stable but useless configurations. Yet in environments where sulfur seeps from volcanic vents or iron leaches from basalt, something shifts. Sulfur and iron act like molecular matchmakers, stealing oxygen atoms from phosphorus and leaving it reactive, desperate to latch onto anything nearby. This process, called phosphorylation, is the same one your cells use today to tag molecules for energy transfer or signaling. The fact that modern biology still relies on this ancient trick suggests these volcanic phosphorus factories weren't just incidental. They might have been the training grounds where life learned its first biochemical reflexes. The implications stretch beyond Earth. Mars' Jezero crater, now explored by the Perseverance rover, contains phosphate-rich minerals strikingly similar to those in the Pilbara. Venus' highland regions, though hellish today, may once have hosted similar phosphorus delivery systems during its brief watery phase. Even icy moons like Enceladus, with their subsurface oceans churned by hydrothermal activity, could be hiding phosphate reserves in their rocky cores. Phosphorus isn't just a terrestrial fluke. It's a universal bottleneck, and wherever nature finds a way to set it free, the path to complexity opens just a little wider. Yet for all its importance, phosphorus has a dark side. Too much of it and reactions spiral out of control, creating messy, unstable molecules. Early Earth's rare phosphorus oases likely struck a delicate balance, enough to spark innovation, but not so much that chaos reigned. It's a lesson written in the rocks. Life's origins weren't just about abundance. They were about precision, about the universe carving out just the right niche where its rarest ingredient could shine. Some molecules don't need instructions to organize, they just know. Picture a drop of oil in water, how it naturally beads up, or soap bubbles forming perfect spheres without anyone blowing them. This isn't just physics, it's the universe's knack for self-assembly, where simple components spontaneously arrange into intricate structures purely by following their chemical instincts. In the primordial chaos, this quiet phenomenon might have been the missing link between random chemistry and the first whispers of life. Take lipids, those humble molecules with a split personality, a water-loving head and a water-fleeing tail. Toss them into a pool and something magical happens. The tails huddle together to escape the water, while the heads face outward, creating a two-layered sheet. Bend that sheet into a sphere, and suddenly you've built a primitive cell membrane, a barrier that separates inside from outside. Lab experiments show this isn't theoretical. Under the right conditions, lipid membranes form effortlessly, even encapsulating other molecules, a rudimentary version of how modern cells package their contents. It's as if the universe baked organization into the recipe of matter itself. But lipids aren't the only self-assemblers. My cells, tiny clusters of molecules that resemble microscopic burrs, behave like molecular janitors. In water, their hydrophobic cores trap greasy substances while their water-friendly exteriors keep them dissolved. On early Earth, my cells might have corralled loose organic compounds, concentrating them until reactions became inevitable. Some researchers believe these structures could have acted as proto-enzymes, their surfaces providing just the right geometry to nudge molecules into bonding. The beauty, no blueprint required, just the quiet tug of chemistry pulling order from disorder. The real genius of self-assembly lies in its scalability. From the lipids in your cells to the silica skeletons of diatoms, nature uses this principle everywhere. Even viruses, those minimalist parasites, rely on it. Their protein coats snap together like Lego bricks without any external guidance. If such sophistication emerges from simple rules, imagine what could have happened over billions of years in Earth's molecular soup. Critics argue that self-assembly lacks direction. How could random structures lead to something as precise as life? But randomness might be the key. In a vast ocean of trial and error, the most stable configurations persist while flawed ones dissolve. It's not a single eureka, moment, but a slow winnowing of possibilities where chemistry becomes architecture simply by playing the odds. This theory doesn't just explain life's origins, it redefines them. If molecules can build complexity without a builder, then the universe might be less a construction site and more a dance floor where particles find their partners through an ancient, invisible rhythm. From lipid membranes to cosmic dust, the same rules apply. When the music's right, order emerges all on its own. Comets are more than just celestial snowballs. They're cosmic time capsules, preserving some of the universe's oldest chemistry in their frozen hearts. When these wanderers swing close to the sun, their icy shells begin to crack and vaporize, releasing geysers of gas and dust into space. But hidden in those shimmering tails might lie the answer to one of life's greatest mysteries: how complex molecules survived the harshness of space to seed planets like Earth. The Rosetta mission study of Comet 67P changed everything. As the spacecraft orbited this duck-shaped ice mountain, its instruments detected 16 different organic compounds, including glycine, the simplest amino acid, and phosphorus, a key ingredient for DNA. These weren't random contaminants, they were proof that comets are molecular factories, assembling life's building blocks in the deep freeze. What makes comet ice so special is its layered history. Far from the sun, temperatures hover near absolute zero, allowing delicate molecules to form without immediately breaking apart. Cosmic rays and ultraviolet light, while destructive, also provide the energy needed to drive reactions on dust grains trapped in the ice. As the comet tumbles through space, these processes continue for millennia, building complexity one collision at a time. Then, when the comet's orbit brings it closer to stellar heat, the outer layers sublimate, revealing fresh ice that's been shielded from radiation-pristine material bearing the chemical fingerprints of deep space chemistry. Rosetta's lander, Philae, even discovered organic, rich dirt on the comet's surface, suggesting these compounds don't just float away. They accumulate where melting and refreezing cycles concentrate them. But the real surprise came when scientists recreated comet-like conditions in labs. By chilling mixtures of water, methanol, and ammonia to near absolute zero and zapping them with radiation, they produced a menagerie of organics, sugars, amino acids, even the nuclear base uracil. These experiments revealed something profound. Comet ice isn't passive. Its crystalline structure acts like a molecular scaffold, forcing atoms into precise arrangements that favor complexity. The vacuum of space slows reactions to a crawl, but that's an advantage. With no thermal noise to disrupt them, fragile intermediates have time to find stable configurations before the next cosmic ray arrives to nudge them forward. Critics argue that cometary organics would be destroyed during planetary impacts, but the evidence suggests otherwise. When NASA's Stardust mission collected particles from Comet Wild 2's tail, it found intact amino acids surviving the violent capture process. Even more telling, meteorites, many of which are thought to be comet fragments, routinely contain these compounds. It's as if the universe designed comets to be both creators and carriers, forging molecules in icy solitude before delivering them to warmer worlds. The implications are staggering. Every time a comet grazed early Earth's atmosphere, it could have seeded the planet with prefabricated organic kits. And since comets are common around young stars, the same process might be playing out right now in systems light years away. the universe's first complex molecules didn't necessarily form on planets at all. They might have been sculpted in the frozen hearts of wanderers, waiting for the warmth of a sun to set them free. Imagine a crackling volcanic plain where heat from below turns bare rock into nature's griddle, not for cooking food, but for baking the ingredients of life itself. The prebiotic pizza hypothesis might sound whimsical, but it's a serious scientific idea that compares the formation of early organic molecules to a bubbling, chemical-rich pie. Just as a pizza's toppings caramelize under heat, simple compounds like water, ammonia, and methane could have sizzled on hot volcanic rocks, transforming into something far more complex. The key lies in the unique properties of basalt and other volcanic minerals. Their porous surfaces act like a cosmic cheese, trapping molecules in microscopic crevices where heat and pressure work their magic. Laboratory experiments have shown just how effective this process can be. When scientists simulate volcanic conditions by heating mixtures of simple organic compounds on mineral surfaces, something remarkable happens. Amino acids, sugars, and even nucleotide bases emerge, as if the rocks themselves are chefs orchestrating molecular reactions. The heat doesn't just drive the process, it fine-tunes it. Too little and the molecules remain inert, too much and they burn away, but at the right temperature, somewhere between a simmer and a full boil, the minerals catalyze reactions without destroying the products. It's a delicate balance, one that volcanic environments naturally maintain through their cycles of eruption and cooling. What makes this theory stand out is its simplicity. Unlike elaborate setups requiring tidal pools or interstellar ice, the prebiotic pizza hypothesis relies on geology's most basic forces: heat, rock, and time. Early Earth's volcanic landscapes would have been covered in these natural griddles, each eruption resetting the stage for new chemistry, and just like a pizza, the toppings matter. Sulfur-rich gases from volcanic vents could have acted like seasoning, providing the reactive spark needed to bridge molecules together. Iron and nickel in the rocks might have functioned as molecular spatulas, flipping and stabilizing compounds mid-reaction. Critics argue that such environments would be too chaotic for sustained chemistry, but nature loves a paradox. Volcanic fields aren't uniformly destructive, they're patchworks of extreme heat and sheltered niches. A lava flow might sterilize one area while creating warm, mineral-rich patches nearby where reactions can continue. Over millennia, these zones could have produced a staggering diversity of organics, with the most stable compounds surviving to accumulate in nearby pools or mud pots. The implications stretch beyond our planet. Mars' volcanic plains, like those around Olympus Mons, or the geologically active regions of Jupiter's moon Io, could be hosting similar chemistry right now. If a volcanic griddle baked life's precursors here, why not elsewhere? The universe might be dotted with these molecular kitchens, each quietly following the same recipe. Mix simple ingredients, apply heat, and wait for complexity to rise. So next time you bite into a slice of pizza, consider this: the same forces that melted the cheese on your plate might have once melted atoms into molecules, setting the table for life's grand feast. The prebiotic pizza hypothesis isn't just a cute analogy. It's a reminder that the universe's most profound creations often emerge from the simplest, most ordinary processes. All it takes is the right heat, the right surface, and a cosmic patience for chemistry to rise. Earth's magnetic field is more than just an invisible shield. It might have been the universe's first conductor, orchestrating molecular symphonies in ways we're only beginning to understand. Picture our young planet, its molten core churning like a dynamo, weaving magnetic lines through the air and sea. These lines weren't just compass guides for early life. They could have been invisible scaffolds, nudging charged molecules into precise alignments that favored complexity. The theory hinges on a radical premise. Magnetic fields don't just deflect cosmic rays, they might actively shape chemistry at the atomic level. Laboratory experiments hint at startling possibilities. When exposed to strong magnetic fields, certain molecules exhibit quirks in their behavior, spinning in sync like dancers following an unseen choreographer. Amino acids, for instance, can become polarized, their charged ends twisting to face magnetic north or south. This alignment isn't just aesthetic, it increases the odds of successful collisions, turning random encounters into intentional handshakes. Even water behaves strangely in magnetic fields, forming transient structures that could have sheltered delicate reactions from destructive forces. Early Earth's field, stronger and more turbulent than today's, might have turned the entire planet into a grand magnetic reactor. The speculative mechanisms grow wilder. Some researchers propose that magnetized mineral grains, like tiny compass needles, could have clustered along field lines, creating highways for molecular transport. Iron-rich clays, common in volcanic regions, might have amplified local fields, turning tide pools into molecular assembly lines. There's even evidence that magnetic fields can influence chirality, the handedness of molecules, potentially explaining why life overwhelmingly favors one mirror image form over another. It's as if the planet itself had a subtle bias, quietly steering randomness toward order. Critics counter that magnetic fields are too weak to directly bond atoms, but indirect effects could be game changers. Fields might have shielded prebiotic molecules from destructive solar winds or concentrated iron particles to catalyze reactions. The most compelling data comes from extremophiles, modern microbes that navigate using magnetite crystals. If life today harnesses magnetism so precisely, why couldn't ancient chemistry have exploited it first? The implications ripple beyond Earth. Mars once had a magnetic field, and its remnants linger in rusty rocks. Exoplanets with molten cores might host similar invisible scaffolds, turning their atmospheres or oceans into cosmic Petri dishes. The universe isn't just built on chemistry, it's conducting it with magnetic fields as the silent baton. Whether this theory holds or not, one truth emerges. The forces we barely notice could have been the architects of everything. Titan, Saturn's largest moon, is a world where chemistry takes on an almost dreamlike strangeness, a place where rivers of liquid methane carve valleys into icy bedrock and hydrocarbon lakes stretch for hundreds of miles under a smog-choked sky. Yet within this alien landscape, scientists see eerie echoes of Earth's own infancy. The same processes that might have brewed life's precursors in our planet's ancient oceans could be playing out right now on Titan, but with methane standing in for water and bitter cold replacing Earth's warmth. It's a looking-glass version of prebiotic chemistry, proving the universe's recipe for complexity is more versatile than we ever imagined. These methane lakes aren't just passive pools, they're dynamic chemical reactors. When sunlight filters through Titan's hazy atmosphere, it triggers reactions in the liquid methane and ethane, breaking them apart into reactive fragments like methyl and ethyl radicals. These fragments, hungry for new bonds, could recombine into heavier hydrocarbons or even nitrogen-containing compounds when they encounter the Moon's abundant organic haze particles raining from above. Cassini's radar scans detected molecules like acrylonitrile in Titan's lakes, a compound capable of forming stable membranes in liquid methane analogous to how lipids assemble in water on Earth. It's as if Titan is running a parallel experiment, testing whether the steps toward complexity can unfold in a completely different solvent. The parallels with early Earth run deeper than surface chemistry. Titan's lakes experience evaporation and rainfall cycles just like terrestrial water cycles, concentrating dissolved organics along shorelines where tidal forces or seasonal changes leave residues behind. In lab simulations, when scientists mix Titan like hydrocarbons with the Moon's atmospheric tholins, complex organic polymers, they observe spontaneous formation of amino acids and nucleotide bases, albeit with structures adapted to methane's nonpolar environment. These reactions don't require the high temperatures or acidic conditions of Earth's hydrothermal vents. They thrive in Titan's deep freeze, where the sluggish movement of molecules actually reduces destructive side reactions, allowing delicate structures to persist. Yet Titan isn't just a colder echo of Earth. It adds twists to the Prebiotic playbook. Beneath its icy crust lies a global ocean of liquid water kept from freezing by tidal heating. Occasionally, cryovolcanoes might erupt, spewing water ammonia slurries into the surface lakes. This creates fleeting zones where water and hydrocarbons meet, offering interfaces where polar and nonpolar molecules could interact in ways impossible in either liquid alone. Astrobiologists call these environments prebiotic petri dishes, where the diversity of possible reactions explodes. If a molecule can form in both Titan's methane lakes and Earth's ancient seas, it suggests universality, a hint that the path to complexity isn't confined to water's unique properties. The implications ripple beyond our solar system. Exoplanets with thick atmospheres and surface liquids, whether water, methane, or even supercritical carbon dioxide, could host similar chemistry. Titan proves that life-starting materials don't need a cozy, Earth-like cradle. They can assemble in the most unexpected places under rules we're only beginning to decode. While Titan's lakes may never give rise to life as we know it, they stand as a testament to the universe's boundless ingenuity, whispering that the story of life's origins might have countless drafts, each written in a different chemical language. Long before planets took shape, the swirling chaos of a protoplanetary nebula might have been the universe's first chemistry lab, a place where dust and gas conspired to build complexity in the void. Picture a vast, spinning disk of material around a young star, its particles colliding in slow motion, each grain of silicate or carbon no larger than a smoke particle. To our eyes, it's a lifeless cloud, but zoom in, and these microscopic motes become cosmic workbenches, their surfaces hosting reactions that defy the emptiness of space. This is gas grain chemistry, where the building blocks of life didn't wait for planets to mature. They got a head start in the nursery of starlight itself. The magic happens in the icy mantles coating these dust grains. In the frigid heart of a nebula, temperatures hover just a few degrees above absolute zero, allowing molecules like water, carbon monoxide, and ammonia to freeze onto every available surface. These ices aren't static, they're dynamic, reshaped by the faint energy of starlight and the occasional cosmic ray. When a high-energy particle slams into a grain, it blasts apart molecules in the ice, creating reactive fragments that skitter across the surface until they collide and fuse into something new. Telescopes have caught this process in action. In the Orion molecular cloud, astronomers have detected signatures of methanol, formaldehyde, and even glycolaldehyde, a simple sugar, clinging to dust grains. These findings aren't anomalies, they're snapshots of a universal assembly line where the raw materials of biology take shape long before worlds are born. What makes this theory so compelling is its scalability. A single nebula contains trillions of dust grains, each one a potential factory for organic synthesis. Over millions of years, as these grains collide gently in the nebula's turbulence, their icy coatings mix and react, building complexity step by step. The process is slow but relentless, like a cosmic 3D printer constructing molecules atom by atom. Lab experiments mimicking these conditions have produced startling results. When scientists chill simple gases to near absolute zero and irradiate them, they watch amino acids and nucleobases emerge as if by magic. The icy grains aren't just passive substrates, they're active participants. They're crystalline structures guiding molecules into precise arrangements that favor order over chaos. But gas grain chemistry doesn't just explain how molecules formed, it also solves the mystery of how they survived. In the vacuum of space, newly minted compounds are vulnerable to destruction by UV radiation. The icy mantles act as shields, absorbing harmful energy while preserving the delicate products within. And when these grains eventually clump together to form comets or asteroids, they deliver their molecular cargo intact to young planets. The Murchison meteorite, packed with amino acids, is a fossilized relic of this process, proof that the nebula's chemistry didn't vanish, it hitched a ride to Earth. The implications are staggering. Every young star system we've observed, from the twirling disks of Taurus to the fiery birthplaces of TRAPPIST-1, shows the same chemical fingerprints. If gas grain chemistry is universal, then the universe didn't just stumble upon life's ingredients, it had a blueprint written in the icy dust of its earliest moments. The nebula that birthed our solar system wasn't just a cradle for planets, it was a kitchen quietly stirring the pot of existence before Earth even had a name. Water doesn't always play by the rules, especially when heat and pressure push it past its breaking point into a strange, almost alien state known as supercritical water. Picture the depths of a hydrothermal vent, where temperatures soar beyond 370 degrees Celsius and pressures crush down with hundreds of times the force of Earth's atmosphere. Here, water undergoes a radical transformation, becoming neither fully liquid nor gas but something in between, a supercharged solvent capable of dissolving rock, reshaping molecules, and rewriting the rules of chemistry itself. This bizarre phase of water might hold the key to how the universe's first complex molecules emerged from the chaos of early Earth. Supercritical water behaves like a molecular alchemist. Under normal conditions, water dissolves salts and polar compounds but leaves oils and organic molecules untouched. Flip it into its supercritical state, and those limits vanish. It suddenly dissolves fats, hydrocarbons, even gases like oxygen and methane with eerie efficiency. The reason lies in its structure. The extreme conditions strip away water's familiar hydrogen-bonded networks, turning it into a free-for-all of single molecules zipping around at incredible speeds. This chaotic environment doesn't just dissolve organics, it tears them apart and reassembles them into new configurations. Lab experiments have watched supercritical water break down cellulose, the tough fiber in plant walls, into simple sugars in seconds, a process that would take years in ordinary water. If it can do that to modern plants, imagine what it could have done to the simple carbon compounds floating in Earth's ancient oceans. Hydrothermal vents are nature's supercritical reactors. Along mid-ocean ridges, seawater seeps into cracks in the crust, gets superheated by magma, and erupts back into the ocean as a scalding, mineral-rich brew. Modern vents like the Lost City Field host conditions where supercritical water likely lurks just beneath the seafloor, hidden in porous rock matrices. These zones aren't just theoretical. Deep-sea probes have detected chemical signatures hinting at reactions only possible in supercritical states. For instance, formic acid, a simple organic compound, forms readily when carbon dioxide meets supercritical water laced with tiny amounts of metal catalysts like nickel or iron. The same process could have churned out precursors to amino acids or lipids in Earth's youth, with vent minerals acting as built-in reaction guides. The beauty of supercritical water is its dual nature, destroyer and creator in one. While it dismantles some molecules, it provides the energy and environment for others to form. Unlike the gentle, stepwise chemistry of tide pools or clays, supercritical reactions are explosive and immediate, offering a shortcut to complexity. Some researchers speculate that fatty acids, crucial for cell membranes, might have first linked together in these extreme conditions, their chains elongating under the relentless push of heat and pressure. Even nucleotides, the building blocks of RNA, could have found stability here. Supercritical water's ability to dissolve both organic and inorganic compounds might have allowed phosphate groups to attach to sugar molecules, overcoming a major hurdle in prebiotic chemistry. Yet supercritical water isn't without its paradoxes. How did delicate organic products survive once they left the high-pressure zone and encountered cooler ocean water? The answer might lie in the vent's architecture. As supercritical fluids mix with colder seawater, they create gradients where newly formed molecules can quickly quench and stabilize. Minerals spewed from vents could have acted as protective carriers, ferrying organics to safer environments where they could accumulate. It's a cosmic version of a factory assembly line. Raw materials enter the supercritical zone, react at lightning speed, then rush to cooler areas before the very conditions that created them can destroy them. This theory doesn't just apply to Earth. Jupiter's moon Europa, with its suspected subsurface ocean and hydrothermal activity, or Saturn's Enceladus, where geysers blast water into space, could harbor their own supercritical nurseries. The universe might be teeming with these hidden crucibles, turning the most unassuming liquid into an architect of complexity. Whether in the depths of an alien ocean or the fractured crust of our own planet, supercritical water proves that sometimes breaking the rules is exactly what it takes to build something new. Among the countless theories about life's origins, one stands out as both radical and elegant: the idea that before cells, before proteins, even before DNA, the molecular stage belonged to RNA. This is the RNA world hypothesis, a vision of early Earth where strands of ribonucleic acid acted as both blueprints and builders, storing genetic information while also catalyzing the reactions needed to copy themselves. But here's the twist: RNA is complex. Its nucleotides adenine, guanine, cytosine, and uracil are intricate structures, each requiring precise assembly from simpler molecules. So how could such sophistication emerge from the chaos of primordial chemistry? The answer might lie in a series of cosmic coincidences where ordinary processes conspired to create extraordinary complexity. Start with the raw materials. Nucleotides don't form easily. They're built from three components: a nitrogenous base, a sugar ribose, and a phosphate group. Each piece presents its own puzzle. Take ribose, for example. In lab experiments simulating early Earth's conditions, this sugar emerges when formaldehyde, a simple molecule found in space, undergoes a series of reactions called the Formose cycle. But ribose is notoriously unstable, prone to breaking down in water or reacting with other chemicals. So how did it survive long enough to become part of RNA? The answer might be minerals like borate, which latch onto ribose and shield it from destruction. On ancient Earth, boron-rich clay deposits could have served as ribose nurseries, stabilizing the sugar long enough for the next step in the dance. The nitrogenous bases pose their own challenges. Adenine, for instance, can form when hydrogen cyanide, a deadly poison to us but a common molecule in space, is exposed to ultraviolet light or lightning strikes. Remarkably, frozen mixtures of hydrogen cyanide and ammonia, zapped with energy to mimic cosmic radiation, spontaneously generate adenine in lab settings. Uracil, another RNA base, forms just as readily from simpler precursors like cyanocetylene, a compound detected in interstellar clouds. These discoveries suggest that the universe has a quiet bias toward building the pieces of RNA, scattering them like cosmic breadcrumbs across stars and planets. But even with the right ingredients, polymerization linking nucleotides into chains seems impossible without enzymes to guide the process, or so we thought. Recent experiments reveal that wet-dry cycles, like those in tidal pools or geothermal fields, can drive nucleotide bonding. When RNA components concentrate in evaporating puddles, the water's retreat leaves them pressed together on mineral surfaces, close enough for chemistry to take over. Certain clays, like montmorillonite, not only bring nucleotides into alignment but also act as catalysts, lowering the energy needed for bonds to form. The result: short RNA strands emerging without a single enzyme in sight. The real magic of the RNA world hypothesis isn't just that RNA could form, it's what it could do afterward. Unlike DNA, which is a passive archive, RNA folds into intricate shapes that let it perform chemical tricks. Some RNA strands, called ribozymes, can cut and join other RNAs. In labs, scientists have even engineered ribozymes capable of copying themselves, a ghostly echo of life's first replicators. This duality, information storage and action in one molecule, makes RNA the ultimate candidate for life's precursor. It's as if the universe distilled biology's essence into a single, versatile polymer, waiting for evolution to take the reins. Critics argue that RNA is too fragile to have survived Earth's harsh early environment. Yet nature thrives on imperfection. The first RNA strands wouldn't need to be long or flawless, just stable enough to replicate occasionally, with errors introducing the variation that natural selection could act upon. Over millennia, these rough drafts might have refined themselves, eventually giving rise to the more robust systems of DNA and proteins. The beauty of this theory isn't just its explanatory power, it's the way it ties together seemingly unrelated cosmic processes. From interstellar clouds brewing hydrogen cyanide to tidal pools concentrating nucleotides, the universe seems wired to nudge chemistry toward RNA. Even today, RNA's fingerprints linger in every cell. The ribosome, the machine that builds proteins in all living things, is fundamentally an RNA enzyme. It's a relic of that ancient world, a molecular fossil whispering that life's origins might still be written in our genes. If the RNA world is correct, then every organism on Earth carries a fragment of that first fragile spark, a testament to chemistry's quiet, persistent climb toward complexity. The vast darkness between stars isn't empty, it's alive with chemistry we can barely comprehend. Drifting through the cosmos like silent giants, dark molecular clouds are cosmic nurseries where temperatures plunge near absolute zero and light struggles to penetrate. Yet within these frozen shadows, telescopes have detected a menagerie of complex molecules: ethanol, formaldehyde, even vinyl alcohol. How these intricate structures assemble in such frigid, light-starved voids defies conventional chemistry and hints at processes we're only beginning to unravel. These clouds operate under rules that turn our understanding upside down. On Earth, heat drives reactions, but in the depths of interstellar space, particles move sluggishly, often taking years to collide. Under these conditions, bonds should form at a glacial pace, yet somehow molecules with dozens of atoms emerge. The secret might lie in cosmic dust. Microscopic grains suspended in the clouds act as cosmic workbenches, their icy surfaces providing a stage where atoms can linger just long enough to connect. When a stray hydrogen atom lands on an ice-coated grain, it doesn't bounce off, it sticks, skittering across the surface until it meets a partner. Over centuries, these slow-motion dances build complexity one bond at a time. Radiation plays a paradoxical role. While intense starlight would shred delicate molecules, the faint glow of cosmic rays, high-energy particles streaking through space, provides just enough energy to nudge reactions forward without obliterating the products. Laboratory experiments mimicking these conditions have produced startling results. When scientists chill gas mixtures to near absolute zero and bombard them with radiation, glycine, the simplest amino acid, forms spontaneously. It's as if the universe hard-coded a backdoor into chemistry, allowing complexity to emerge where it logically shouldn't. Yet mysteries abound. Telescopes have spotted molecules like dimethyl ether and acetic acid in these clouds, structures so complex they rival precursors to life's building blocks. Some theories suggest quantum tunneling, where particles bypass energy barriers entirely, could explain their formation. Others propose that shockwaves from nearby supernova or young stars briefly heat pockets of gas, creating temporary zones of intense chemistry. The truth might be a combination, a delicate interplay of ultra-cold surfaces, weak radiation, and patience on a cosmic scale. Studying these environments is like trying to decipher a whisper in a hurricane. Traditional spectroscopy struggles to distinguish molecules in the crowded fingerprints of distant clouds. New tools like the Atacama Large Millimeter Array now peer deeper, mapping chemical factories light years wide with unprecedented resolution. Each discovery raises new questions. Are these molecules stable enough to survive until planet formation? Could they have seeded Earth with pre-made organic kits? The most tantalizing clue lies in meteorites. Many contain amino acids with isotopic signatures pointing to origins in interstellar space. If dark clouds are indeed universal chemists, then life's raw materials might be older than planets themselves. A cosmic inheritance written in the language of frozen dust and silent reactions. These clouds remind us that the universe thrives in contrasts. In the coldest, darkest corners where time stretches thin and energy is scarce, complexity finds a way. What seems impossible becomes inevitable given enough time, a few starlit particles, and the universe's quiet persistence. Lightning steals the spotlight when we imagine electrical forces shaping early Earth, but it wasn't the only player in the planet's grand power grid. Beyond the familiar crackle of thunderstorms, lesser-known electrical phenomena, coronal discharges, auroras, even the faint crackling of dust storms could have been unsung architects of molecular complexity. Picture Earth's atmosphere 4 billion years ago, a turbulent sea of charged particles and swirling gases. High above the surface, where oxygen was scarce and nitrogen dominated, faint violet tendrils of electricity called coronal discharges flickered along mountain peaks and volcanic plumes. These ghostly sparks, far weaker than lightning but far more persistent, might have provided the steady trickle of energy needed to nudge simple molecules toward sophistication. Lab experiments reveal just how potent these subtle discharges can be. In a sealed chamber filled with methane, ammonia, and water vapor, gases thought to dominate Earth's early air, scientists applied low-voltage electrical currents mimicking coronal effects. Instead of violent explosions, they observed a slow, methodical synthesis, amino acids forming at rates comparable to lightning-driven reactions but with fewer destructive side effects. The key was the gentler energy profile. While lightning blasts molecules apart as often as it bonds them, coronas offer a Goldilocks zone, enough energy to overcome activation barriers, but not so much that products shatter before they can stabilize. It's the difference between smashing atoms with a sledgehammer and coaxing them together with a whisper. Then there are auroras, those shimmering curtains of light dancing near the poles. Today, they're fueled by solar particles, but early Earth's stronger magnetic field and more active sun would have made them a global phenomenon, not confined to high latitudes. Auroras don't just glow, they rain electrons down into the atmosphere, creating cascades of ionization that could have reached the surface. In simulations, electron beams directed at prebiotic gas mixtures produce hydrogen cyanide and formaldehyde, two critical precursors for nucleobases and sugars. Unlike lightning or coronas, auroral electrons penetrate deeper into gas layers, initiating reactions in regions where UV light and heat would normally destroy fragile organics. Even dust storms played a role. In arid regions, swirling silica particles build up static charges through friction, creating tiny sparks invisible to the eye but potent enough to alter chemistry. Modern desert storms generate measurable quantities of hydrogen peroxide. This way, a molecule that, despite its destructive reputation, can drive the synthesis of complex organics when carefully controlled. Early Earth, with its vast volcanic deserts and thinner atmosphere, might have crackled with these microscopic discharges, turning dust clouds into sprawling chemical reactors. The brilliance of these lesser-known electrical processes lies in their ubiquity. While lightning demands specific atmospheric conditions, coronas, auroras, and dust sparks operate across diverse environments, from mountaintops to tidal flats, poles to equator. Together, they form a distributed energy network, ensuring no corner of the planet was entirely starved of the jolts needed to spark complexity. The universe doesn't rely on grand gestures to build life. Sometimes it's the sum of a million tiny sparks that lights the way. Deep beneath the ocean's surface, where Earth's crust cracks open like an eggshell, A silent alchemy transforms ordinary rock into a fountain of hydrogen, a process so potent it might have kick-started life itself. This is serpentinization, a reaction so fundamental yet overlooked, where water seeps into fractures and meets olivine, a mineral common in Earth's mantle. The encounter is anything but passive. The water steals oxygen and iron from the olivine, leaving behind a greenish mineral called serpentine. But the real magic lies in the byproducts, hydrogen gas and fluids so alkaline they could dissolve flesh. To us, these conditions sound hostile, but to the universe's first molecules, they might have been the perfect crucible. The chemistry is deceptively simple yet revolutionary. As hydrogen bubbles from the rocks, it doesn't just float away, it becomes fuel. In lab experiments mimicking these environments, hydrogen reacts with carbon dioxide to form formate, a precursor to more complex organics like acetic acid. The alkaline fluids, rich in hydroxide ions, create a gradient where protons are scarce, effectively acting like a natural battery. This isn't just random chemistry. It's a self-sustaining system where the very process that generates energy also drives molecular complexity. Some researchers believe these gradients could have powered the first metabolic reactions, bridging the gap between geology and biology. Lost City, a ghostly white vent field in the Atlantic, offers a living glimpse into this ancient process. Unlike the sooty black smokers of other hydrothermal systems, Lost City's chimneys are built from carbonate minerals, their porous structures dripping with alkaline fluids. Here, scientists have detected organic molecules like methane and formate forming abiotically. No biology required. Even more astonishing, the vent's labyrinth of micropores and channels acts like a molecular sieve, concentrating reactants while shielding fragile products from the surrounding acidic ocean. It's a natural refinery where physics and chemistry conspire to turn rock and water into life's raw materials. Critics argue that alkaline vents lack the phosphates or nitrates needed for nucleotides or amino acids, but nature is resourceful. Nearby volcanic activity could have supplied these elements, mixing with vent fluids in shallow pools or tidal zones. Others point to the vent's mineral chimneys, which contain tiny compartments resembling primitive cells. These geological protocells might have provided the first enclosed spaces where molecules could interact without being diluted into oblivion. The implications stretch beyond Earth. Mars' ancient crust contains olivine-rich regions, and Europa's seafloor likely hosts similar chemistry beneath its icy shell. If serpentinization could coax complexity from rock here, why not on worlds where oceans churn in darkness? The universe might be dotted with these silent factories, turning the most ordinary stones into cradles for the extraordinary. From volcanic griddles to quantum tunneling, cosmic rays to tidal pools, the journey to uncover life's first molecules is as diverse as the cosmos itself. Each theory we've explored isn't just a standalone idea, it's a piece of a grander puzzle, a single thread in the universe's tapestry of chemistry. Maybe life didn't begin in one place or through one process, but through countless experiments playing out simultaneously across Earth's ancient landscapes and beyond. Picture a symphony where hydrothermal vents provide the bass line, electric sparks add percussion, and interstellar dust delivers the melody. Together, they compose the soundtrack of existence. Which of these theories speaks to you? Do you see life sparking in the violent collisions of meteorites or quietly assembling in the icy silence of space? Perhaps it's the rhythmic dance of tidal pools or the relentless churn of deep Earth chemistry that feels most compelling. There are no wrong answers, only possibilities waiting to be tested, debated, and dreamed about. That's the beauty of science. It's a conversation, not a conclusion. So share your thoughts below. Which origin story resonates with you and why? The mystery of life's beginnings isn't just about the past. It's a gateway to understanding our place in the cosmos. If molecules could defy the odds on Earth, what else might be possible on distant worlds? The universe is brimming with unanswered questions, from the enigmas of dark matter to the secrets of time itself. If you've enjoyed this deep dive into the origins of complexity, don't miss our next adventure. Hit subscribe and let's keep unraveling the cosmos together, one theory, one discovery, one cosmic whisper at a time. The journey has only just begun.